Hey, okay, welcome back here, everybody, and yeah, come on in. So you in-person people and you online people, let's actually get started in physics. As you probably recall from yesterday, we did our first chapter, which was more what I call a science chapter, you know, converting units and significant figures. But now let's actually start with our physics. And so I'm going to jump right in here and say, all right, let's do kinematics. And so that's where I want to begin here. So I'm going to put here on the board here for chapter 2, we're going to do what we call one-dimensional kinematics. And so kinematics just means motion. And so we're going to start talking about things that move. You know, maybe it goes left or right, maybe it goes up or down, maybe even it goes down an incline, but it's only going to be one-dimensional. Well, here's what we mean by one dimension, because sometimes that can get a little confusing. I mean, here I have a ball, and so by motion, what I mean is it changes its position. You know, it moves. And then we're going to, of course, introduce some words that you probably were already somewhat exposed to, and that's what makes this a good place to start physics. It's the kind of the basic thing. We'll talk about speed and velocity and the difference between them, the difference between average speed and instantaneous speed, acceleration, and again, average acceleration, instantaneous acceleration, and really that's the whole chapter. And so this is a good time for me to say what I started to say yesterday, and you'll probably hear me say on every chapter, physics is about knowing how to apply a few but powerful concepts to explain a universal phenomenon. So the goal here really is just to get you to understand what is speed, velocity, and acceleration, and then how they're connected. And then you'll be amazed at how many different phenomenon we can talk about just on that principle. So that's where we're headed. And that's what's called kinematics. Now, it's called one-dimensional kinematics because, again, we're just going to be moving in one dimension. So something like this, rolling across this table, is one-dimensional. Now, I would call that horizontal because also if I took it and I dropped it, it would be one-dimensional. Now, maybe we'd call this the y-axis and this the x-axis, and so we're going to use a lot of mathematics to describe all of this, and that's, of course, going to be my goal here, is to try to get you to understand the mathematics. And so once we understand the idea of what is speed, velocity, and acceleration and those differences, then we'll put those in equations, and then we'll be able to solve for a lot of motion. But I want to emphasize, when I say one dimension, it doesn't mean horizontal. It may not even mean vertical. This incline is a good example of one dimension. I can start it here and let it go. I wouldn't call this the x or the y-axis, but I would say that it is going in one dimension. It's going along an incline. So we'll probably just kind of take an x-axis and turn it on its side and talk about it that way. And so that's going to be the creativity that I want to get across to you. So when I say one dimension, when I say an x-axis, I don't necessarily mean horizontal. And that's really where I want to start. Now, your author does a good job, and in order to save time, I'm just going to point out the beginning of the chapter where your author says, what's this chapter all about? And I think I kind of just summarized it even more so than your author does. But here he talks about displacement. He talks about vectors and scalars and coordinate systems. He talks about speed, velocity, and time. Goes on to the next page, acceleration, then he gets into the equations, then he gets into solving problems, he gets into more one-dimensional motion by falling or dropping an object, and then of course all of this is involving math, and so math can be described in a graph, and so that's really this goal here for this next hour and a half, is what is the mathematics of all of this speed, velocity, and acceleration. All right, so I'm going to start then kind of where we left off here. If I put it here, well, I'll start it here, but I'll have to continue my chart over here, because I want to tie Today's starting with yesterday's ending. And yesterday we had this. We had a little chart that we said, okay, let's start talking about physics by thinking about the physical world and asking a question. You might remember that on the board here we had the first thing was we talked about distance, or we even used the word displacement. And when it came to the symbol, we said, why don't we call that a delta x? Now let me pause right there, because if I come over here to this third board here and I put a mathematical grid, calling this the x-axis and this the y-axis. And so notice I'm putting 2 dimensions on here. I want to emphasize, we're only talking about 1 dimension right now, but the next chapter is 2 dimensions. Okay, so I might as well kind of just pull your memory out of your math class. Okay, how do you describe a position of an object? And well, in 2 dimensions, you have an x-coordinate and a y-coordinate. Okay, and that's what I want to start doing this morning, is saying, okay, let's go back to your math classes. We're going to use a lot of math tools here to describe our motion. Now, I want to start with just understanding the concept, but eventually the concept's going to turn hopefully into equations, okay? And that's what I've been saying. It's going to be my job to kind of teach you. How do I take an idea and a concept, take that, and then change it into an equation? And then use those equations to figure out, you know, where is the rocket in 3 days, you know? Where is the molecule after a femtosecond, to figure out what the motion is. All right, so I'm going to put a grid on here, and at starters, though, I'm just going to talk about the x-axis. So let's say our object starts here. Let's call this then x naught, referring to as the initial position. And then whatever this object is, a little bit later, maybe it's here at position x. I won't call it final just because I want to give this the option that it's moving, it's changing. So this is the position a little bit later in time. I just don't want to call it its final position. All right, so I've got these 2, but from movement from here to here, I can represent with a little arrowhead. That's the direction it moved. Now, I say all that because if you wanted to know how far it moved, you would just subtract these 2. Fair enough? And then the common symbol for a difference is the delta x. And so this ties back with what we were saying in the first chapter. If I wanted to describe the displacement, I would just take a delta x. I would take the position where it currently is, subtract off where it started. Now, notice, by the way, if it had started here, so maybe in a different color, so let me call this x naught. Maybe it started here, but it moved the other direction. And so maybe a little bit later, it's now here. I might still ask this question, what's its displacement? Where did it go? And it's the same math. I would just say, okay, delta x is the x minus x naught. So whether it moves left or right, that's not going to change my thinking about how do I calculate its displacement, how do I calculate how far it moved. All I do is I take its current location and subtract its initial. But do you see how you'd get a negative number for this one? All right, and so displacement has not only a number of how far did it go, but also what direction did it go. Fair enough? So that's our first step of math. And hopefully that was pretty easy. It's going to get a little harder, but hopefully not hard at all. Hopefully you'll just, oh yeah, this is the same stuff I learned in algebra. Okay, so with that in mind, you can now see why yesterday, when I put some symbols on the board, I said if you're just talking about how far did it go, its distance, not worrying about plus or minus, you would take the delta x and take its absolute value. So somebody asks you what is distance, you don't use a plus or a minus. You just say, well, you know, it moved 5 meters. 5 meters left, 5 meters right. You might talk about it, but you don't really say plus or minus. Now, if you then say the displacement, well, now you're saying, did it go left or did it go right? And of course, the tradition, and we don't have to always stick to tradition, but we might as well, unless there's a reason to leave tradition. Tradition is for the x-axis, it's not only just horizontal, but it's also positive to the right. And so normally, if we have a positive displacement, we'll say it moved to the right. And a negative, we'll say it moved to the left. Like I said, we could change that. Sometimes we do. But for the most part, we don't, because you're so used to that tradition that just adds to more confusion. And it's hard enough. We don't want to add any confusion to what we're about to do. It's going to be tough enough. All right. So that's our starting point here. But it brings up really our first real vocabulary word here. What is a vector versus what is a scalar? And those are just fancy words that are very, very important, but they're just fancy words. Here's what they mean. See, some quantities in physics have to be represented with direction, not just a number. Now, I bet it wouldn't surprise you if I asked you, which is bigger, 10 or 2? Most people go, well, 10 is. Until I say 10 inches or 2 feet. Well, clearly 2 feet is more than 10 inches, right? Okay, so it really depends, not just on the number, but in this case, the units. So I would argue, as we were doing yesterday, that the units are just as important, if not as important or more important. Well, I don't want to say more important as the number, but the number and the units go together. You really can't just say which one's bigger without the units. Fair enough? But in the physical world, I want to argue that direction, for some things, not everything, but for some things, is absolutely important. For example, all of you are, well, you guys in class or you guys online, your car or your transportation is somewhere else right now, okay? In my case, I'm thinking of my car, which is out in the parking lot. It's probably about a quarter mile away. Okay, so I got maybe about 400 meters that way. It's my car. Okay. So the distance is 400 meters. To get to my car, does it matter which way I walk? Is direction important? I mean, if I go 400 meters that way, I'm not going to get to my car. If I could fly and go 400 meters that way, I'm not going to get to my car. And so what's important for me to get to my car is not just how far, but also what direction. How about pushing something? If I wanted to take this cart after the lecture and push it back into our storeroom and get ready for tomorrow, does it matter if I push it to the right versus pushing it to the left? See, it does matter. And that, then, is why we have this fancy word called a vector. A vector is some kind of physical quantity that not only has a number, which I'll call its magnitude, but it also has a direction. And so I would argue here at this beginning step that right here, displacement is a vector. By taking this subtraction, this delta x, I can get a positive or a negative. And it is going to make a difference whether it moved positive or whether it moved negative. And so I would say displacement then is a type of vector. A push or a force, which we'll get to in chapter 4, so that'll be tomorrow, but is going to be a vector. It depends on which way you push it. However, not all physical quantities have a direction. They just have a magnitude. And so we call those scalars. And probably the best one to point out is just time. You know, if we look at the clock and say, okay, now we've been in class for 15 minutes. Does it make any sense to say, oh, 15 minutes to the north, or 15 minutes to the south, or 15 minutes to the west, or 15 minutes to the east. Direction just doesn't come into play for that physical quantity. So time is a scalar. Temperature is also a scalar, right? The temperature outside, it's a nice day. It's right now it's probably about 72 degrees Fahrenheit, but it wouldn't make any sense to say it's 72 degrees Fahrenheit to the left, or to the east, or to the west. Yeah.
Okay, this is a ridiculous question.
Oh, no, there are no ridiculous questions.
Well, hypothetically, if time were to be discovered that there is two directions.
Oh, yeah, right.
Would that remove it from the scalar?
Yeah, so then you would call it a vector.
Oh, okay.
There would be all kinds of weird things, though, in our world.
I've been watching too much Marvel.
Yeah, if time was a vector. So instead of having a direction, it just increases or decreases. But what I just want to get at right here, as we get started in the math, is that we're going to be working along, and we need to point out each time we talk about a new quantity, is it a scalar or is it a vector? Because if it is a vector, well, then we got to think about not just the number and the unit, but also the direction. Whereas something that's a scalar, it's a little easier. So time, temperature, mass is another good one. A human has a mass of about 70 kilograms. Human doesn't have a mass of 70 kilograms to the left. It doesn't make any sense. But there is a push to the left and a push to the right, and they're different. A push to the left and a push to the right are definitely different. All right, well, again, let me keep going, because I want to kind of tie today with yesterday, and I think that helps here. And so this displacement is really a vector, and it was going to play a bigger role when we get into moving in two dimensions. And so that's why we get started here. Now, just for completeness, you might remember we had then area, which we had symbol A. Then we had this idea of volume. I'll just abbreviate and say volume. But I want to point out what we were doing is we started with a distance or a length, and then we kind of thought about a new feature. And in our case, we were doing like the surface area of that desk. And then we wanted to know the cabinet space underneath it. So we kind of kept asking the next physical question. Now, we also had on here mass and time. And on the other side, of course, was the units to measure them. And the symbols. Let me not fill in this chart, but I want to continue now for today and say, all right, what is our next question? What is our next physical quantity that we might ask ourselves? And maybe the first one I've already touched on, and it probably actually fits better into this category, so maybe I can squeeze it in. But did you see here, I really had 3 different indications of x. I don't know if you caught that. It was so subtle. I have x minus x naught, which I called the displacement. I had the distance, which was just the absolute value. But did you notice I was measuring everything from some chosen origins, someplace that I could pick? So in other words, the x was actually the position of it. Now this is what I called then this one here I called the initial position, and then the final position, and I subtracted those two. So I should probably squeeze that in here and say, all right, kind of along these lines is a term called position, and we'll just label it with an X. And of course, not a surprise, it would be measuring a distance, so it would be in meters. But did you notice then that it's measured from some origin? So here's what's interesting. The origin then is where you guys, as you do a problem, have that freedom to pick where do you want to call x equal to 0, right? You could say, let's measure everything from this wall. And then you could measure the edge of this table to the edge of this table, as I was doing yesterday. I got to admit, most of the time, it's probably easier to call the initial the origin, and that way you have a 0 as your first spot, and that's what I'm going to encourage you to do. But you don't have to do that, because no matter where I pick the origin, I could pick the origin to be that wall, I could pick the origin to be this edge, I could pick the origin to be this edge, I could pick the origin to be this edge. The origin in the coordinate system is a human choice, but the size of that table is not. Do you see that difference? And so if I pick the origin right here, I'll say one edge is 0 and the other edge is about 2. And so I'd say, well, the table's 2 meters long. But if I picked this wall to be the origin, well, then I'd say, okay, well, this edge here is 4 meters and this edge is 6 meters. And if I want to know the size of the table, I'd go 6 minus 4 is still 2, no matter where I picked that origin. So there is a little subtlety there, but an important one, because I have noticed that sometimes that's where students make their errors at the beginning. They kind of confuse what is the position, what is the difference of the position. Okay? And so I just want to point out, we've got position, which can vary depending on individual people where they pick the origin. So I'm going to encourage you, when you start a problem, go out of your way to mentally say, where am I going to pick the origin? And I would encourage you to pick it which makes the problem the easiest. Don't make the problem harder on yourself. But know this, it wouldn't matter, because you're still going to get the same physical answer for the size of that table. And I know when I'm grading papers and I'm grading tests, that's one of the first things I do. I said, okay, where is this student putting the origin? Because it varies so much from student to student. And there isn't a right way or a wrong way. I just need to know where the student is doing it. The real problem comes in when the student halfway through the problem incorrectly calls a new origin after they've done these calculations, and things just go bizarre in the problem because they've kind of forgotten where they've called x equals to 0. So that's my beginning warning for you. Make sure you consciously pick where I'm going to do the origin, and then you can follow through on the problem. And so make an extra effort for that. And you'll see when I do examples here, that's what I'm going to do. I'm saying, okay, where am I going to pick the origin? I'll even ask you, where do you guys want me to pick it? Which will help emphasize that you can pick it anywhere you want. All right, so, excuse me. So that's kind of the first, and I'll call it a new quantity for today, but it fits right in here. So if we're looking at something now that is moving, we might ask this question. Let's take the moving object as me. Okay. So I'm going to start right here, but I'm going to make a conscious effort and call that wall over there the origin. Okay, so that's 0. Okay, so I'm going to start right here. So I'm starting maybe about 4 meters away if you wanted to give me a number, but this is going to be my starting point. And let's just say I'm moving across the room. And when I get all the way over to here, this wall is about 12 meters away. All right, so I went from 4 meters to 12 meters, and that's what we've been talking, but now we might ask this. How quickly did I go from here to there? This is what we would call a rate. And so I think you've kind of already done problems like this. What am I really asking about? Yeah, I'm really asking something like, okay, how much distance, or maybe even how much displacement did I travel per second? See, that's what I'm asking. I'm asking my rates. I'm saying, when I went from here, which was about 4, over to here, which is about 12, did it take me 1 second? Did it take me 2 seconds? Did it take me 3 seconds? And so it's not just that I moved. Clearly, I moved from 4 to 12. And if I wanted to know my displacement, I'd go 12 minus 4, which I guess is 8. But another question is, how quickly did I do that 8? Did I do that 8 in 1 second, or did I do it in 2 seconds, or did I do it in 3 seconds? And so all of this is our first step of this chapter, our first quantity. Yeah?
So considering that displacement can technically be negative, would that be not a way to approach that problem?
So I'm going to do this. I'm going to call this a fancy word, which I'm sure you heard, speed. But I'm going to call this velocity. So speed and velocity are our new word here for this moment. They are slightly different, right? So the speed, as you can correctly see, and I'm glad you guys saw that, the speed is just distance divided by time. It's just the rate, it's just the number, it doesn't include the direction. I would call speed then the scalar, or you might say speed is just the magnitude part of velocity. And so really then we're going to focus most of our attention then right here on V for velocity. And if we only want to know its speed, maybe we will just do something like that. We'll just say, hey, just give me the absolute value of the velocity. Especially here at the beginning, because at the beginning we're just going left and right. And that means our velocity is just to the right, positive, or to the left, negative. Okay? But this does answer, hopefully, a couple of questions here. And the first one is, what is speed and velocity? What is this definition? And the second one, then, is what is the difference between them? And there's not much of a difference. That's why sometimes we carelessly use them interchangeably. But technically, they're not the same. And that's what I want to emphasize. Technically, velocity does have a direction. It is a vector part of it. And so that's kind of this emphasis on this word. It's a vector, okay? Well, you can then kind of see here that if I wrote this down as an equation, and let me just focus on velocity, because I think speed, you're going to see the same thing, it just wouldn't have a direction. I would write it this way. I would say velocity then is the change in the position over, now here's an interesting one, time. By time, do I really mean the 8:30 on the clock? Right, and so what I really mean is the time it took me to go from here over to there. So maybe I started at 8:30, but by the time I got over here, maybe it's 8:30 and 10 seconds. So it took me 10 seconds. So I'm going to then, not a surprise I hope, put delta t right there. Oh, and I guess I didn't follow my little pattern here. I should have put a slash to say, okay, what are the symbols? And I put them over here. So I'm going to put absolute value of v and v, okay? But now I want to get into what I talked about last time, is that once you hopefully kind of come up with a new thought. And that's what I'm trying to help us lead through, a new thought. The thought is position and moving position, changing position. So it's the rate of how you moved your position. That is our new thought. And I say new thought, but this is a good place to start, because I have a feeling speed and velocity are not new to any of you. You've been in a car, you've been on a bike, you've been walking. You kind of have already a feel for this first one here. But if you remember me talking about these 4 steps, the first step is give me a new thought. Give me something you're thinking about, and that's going to be our new physical quantity, which will lead to an equation. And so had you never seen this equation before, you would be able to work it out yourself. Isn't that what I was saying yesterday about area? I said, yeah, you did area back in 5th grade. And I'm just going to do the same thing. Even though you've probably done speed and velocity before, you may even have seen this equation, but I'll say it the same thing. If you'd never seen this equation, you just have a thought. You have a thought of, okay, that object is changing its position. How quickly did it do it? So it's a rate, so I'm going to divide it by time. And so first step is you got a new quantity. The second step is you got a new formula. The next step then is what would be the units for that? And hopefully it's pretty obvious when you look up here. What units would you use up here in the numerator? Yeah, meters or anything related to that, like centimeters or kilometers, but I'll go with meters. Okay, so I'm going to put meters here. And then what would you use in the bottom? A time, probably seconds, but you could use hours or something. So the base units would be meters per second. Most of you probably think in terms of miles per hour, or maybe even kilometers per hour, because that's normally how we have our car speedometer, but they're talking about then a bigger distance and a bigger amount of time, but it's still the same idea. It's a distance per time. So if I told you something like the speed of a car is 2 meters per second, what does that mean to you? Now let me just backtrack, right? This is step 4. I'll say it again. Step 1. Got a new thought of the physical world, which leads to step 2, a new formula, right? Which leads to step 3. What are the units to measure this new quantity? And then the big one is let's study that unit so we can have some physical intuition. And so this is my last step 4 here. What does 2 meters per second mean to you?
Every second goes 2 meters.
Right. In 1 second, you'd go 2 meters. So if I was standing here, maybe going this way 2 meters per second, 1, 2, I would go 2 meters in 1 second. What would happen after the next second? 1, 2. I'd go another 2 meters after that 1 second. And the next second, 1, 2. So after 3 seconds, I would have gone 6 meters because I would have gone 2 meters every second. And if that makes sense to you, then hopefully the rest of this semester and the next semester will. Because this is exactly the game we're going to play. We're going to have a new thought, which leads to a new quantity, step 1. That leads to a formula, step 2. That leads to the units that measure that formula, step 3. And then that leads to a chance to sit back, study the units, and get a physical understanding of what that quantity actually means. And so those 4 steps I'm going to go through over and over again. And this is a good place to start it because just like you were already exposed to area and volume yesterday, you probably were exposed to this. And knowing that 2 meters per second just means it moves 2 meters every second is probably not very enlightening. You knew that. But keep that fundamental in mind because we're going to see things you haven't seen before. And so when we start talking about things you haven't come across before, hopefully they will be as easy as this step. Now, let's go 1 step further here. Because what if I was moving across this room, but at the beginning part, I was going really fast and then I slowed down and went slow. And so if I went this whole distance, so remember, starting here. So if I'm starting here at 4 meters and I go all the way across the room to 12 meters, I might do, okay, he went 8 meters. And let's say it took 4 seconds to do that. You're going to say, oh, it's 2 meters per second. However, if I go really fast and then go really slow, so the total time is 4 seconds. This isn't a complete description of what happened, is it? Because during here, I went way more than 2 meters in 1 second. But over here, I went way less than 2 meters in 1 second. You see what I'm getting at? And you said it well. This then is probably best described as what? Yeah, this is really average. And so if you just take the whole distance and divide it by the whole time, you're going to get an average. And I would say that that can be useful at times. But what I'm trying to lead up to is it might be more useful to keep thinking about a physical quantity. And so I guess it kind of still falls in this category, so I won't add another part to the chart here. But I do want you to realize that there's a difference here in saying, okay, what are you doing at that instant? So let's just talk it conceptually. What do you mean by at that instant? Well, I don't mean the whole 8 meters, right? I mean, what am I doing right now? And it doesn't even have to be a long distance. It could be a short distance. And so what you're really saying here is something to this effect, that your instantaneous velocity would be when you have this delta x and this delta t, but you're talking about a really small number. So a small amount of time. You say, well, what do you do in that short amount of time? It's kind of like your speedometer. Your speedometer is doing the best it can to measure your instantaneous speed. What it does is it measures how much time does it take, and under your car you have this drive shaft and a little magnet, and the magnet spins around, and as it goes around, one revolution of that drive shaft makes the wheel move just a small fraction, and the computer knows how far then the car moved forward because it was one revolution of the drive shaft. And then it can measure that time, and so it can take a very small distance and divide it by a very small amount of time, and then that's what it would display on the dashboard. And so maybe at that moment you're going 55 miles an hour, and then maybe you tap on the brake, maybe the traffic's slowing down, so you tap on the brake, and so that drive shaft goes a little bit slower, and then so the computer recalculates the next revolution. Instead of being 55, now it's 50, and the next one it's 45, and it gives you your instantaneous, or at least close as you can get to instantaneous. What I'm trying to do here is give you then this mental picture that there's two things here. We can talk about the average speed, we can talk about the instantaneous. But I would describe this then in terms of math as calculus. And so let's step up from algebra to calculus. And so this is really those thoughts changed into an equation. So you see what I did? And this is the skill I'm trying to get you to develop. You're taking a thought, which in this case is the rate at which you change your position, and you want to know it instantaneously. Take that thought and change it into an equation. And that's what you come up with. In fact, I'll even take it one step further. The limit as time goes to 0 of this, you would call the derivative. And so dx dt. So here is the equation that I would think about for instantaneous velocity. Whereas this is the equation I would think about for average. And so let's talk about, of course, both of those and see what kind of problems we can have. And I think the best way to really kind of show all this is for me to do examples. So I'm going to do a bunch of examples for you today. But again, I just kind of want to get the ball rolling and say the goal here is to try to get you to understand that difference between speed and velocity, average speed, and instantaneous speed. And there is another step to this. Because in this process of thinking about instantaneous speed or velocity here, didn't my speed have to change? Right? I mean, the example I was giving you was this, that I stand right here at a position of 4 meters, and at first I go really fast, and then I slow down, and then I go really slow. And that's, of course, why we got this average, but we had over here a large instantaneous speed, and over here a slow instantaneous speed. But doesn't that beg the question of how quickly did you change from your fast speed to your low speed? I would call that another rate. In other words, instead of saying at what rate did you change your position, I'm asking at what rate did you change your velocity? And I should have left myself a little more room here, because these are changes in position. This is change in velocity. And of course, as we mentioned before, change in time. And so this is our second quantity. Acceleration. And so what we're going to do then is ask not just how do you change your position, but how do you change your velocity? Now, the symbol, as I mentioned yesterday, is going to be a lowercase a. And so our lowercase a, which is, again, why we wanted to use the uppercase A for area. And also, I should have pointed out the uppercase V for volume, so that we could use the V over here for velocity and the A here for acceleration. But let me do the same thing. I think it is a little bit harder to understand acceleration than velocity, but not too much harder. And I would even say that's kind of the same game we're going to keep playing. We're going to keep asking a next question every chapter, and we'll have a couple of new quantities to think about, and we will begin to understand the physical world more and more and more. And so where in the first chapter we were looking more at space, now we're looking at the rate of change of space, or not space itself, but the object that's in the space. And then we'll be talking about other quantities. But I don't want to get too far ahead of myself. I just want to say that this is the goal. There's not really much in this chapter, but it's deep. And it's some of these problems can be pretty hard, because we could confuse acceleration with velocity. Or we could confuse velocity with speed. Or we could confuse average speed with instantaneous speed. Or we might get tripped up in our math. How do we calculate all these? All right. But I want you just to kind of have these same 4 steps. So step 1. See the new thought? My new question is, how quickly did I change my velocity? Which must lead to an equation. So what would the equation be for acceleration? So acceleration would be what? Change in velocity. Which you might write out as, what is my current velocity minus my, say, starting velocity over the time taken. Now let me just give you some numbers to work with. But let's say, again, back here, I was running really fast. So maybe at this point I was running with a speed or a velocity of 6 meters per second. Okay, so here, I was going 6, and then I slowed way down, and now I'm only going 1 meter a second. Okay, so 1 meter a second. What? I'm sorry, Ron?
You're doing final minus initial, or initial minus final?
Thank you. Yep. My apologies. Thank you for catching that. Yep. All right. So final over. Okay. So 1 minus the 6. So this is going to give me negative 5 meters per second, and then the time. And I'll just make something up to give you a feel. Let's say that going from here over to here took me about 1 second to slow down. Okay, so 1 second. So 1 second. I would then get a negative 5 meter per second over second. Now there's 2 ways really to write this, but let me just point out here that what you heard me say yesterday, I'm going to keep saying. Do the same rules of mathematics for your units as you do your numbers. So you could leave this as meter per second each second. Or, like all compound fractions, let me come over here and remind you, what if I had, say, 2/3 over 7? Don't you go 7 over 1 and make it a compound fraction? And then you flip and multiply. Let me do the same thing with my units. So I will go over 1. I will then flip it, so I will go meters per second times 1 over second, and I will get a negative 5 meters per second squared. So in terms of math, this might be easier. In terms of understanding, I think this might be easier. So over here, in this column where it says what units do we use, I will put both. I will put meters per second each second, but I will also put meters per second squared. And that's step 3, right? Step 1, new quantity. Step 2, a formula that goes with that quantity. Step 3, the units that measure the quantity. And then the big step. What does that mean? What does negative 5 meters per second squared even mean? Well, I think it's probably better to write it this way. What does negative 5 meters per second each second mean?
Every second you're going at the speed negative 5 meters per second.
Very, very close. Not at the speed, you're changing your speed. So in other words, I was going 6. A second later, I would have reduced, there's the negative, by 5 meters per second during that 1 second. So I would have gone from 6 down to 1. And I want to emphasize something. Do you see my acceleration is not the same as my speed? Those are 2 different things, right? See, my speed is a 6 and a 1. My change is the 5. It's so easy to confuse acceleration with speed. They're not the same thing. For example, let's take an airplane that flies over right under the path here of the airplanes. You look up, you see the contrails all the time. And this airplane maybe is flying 400 miles an hour, 400 miles an hour, 400 miles an hour, 400 miles. That is a really large speed, so it must have a large acceleration, right? Now, what would be the acceleration of that airplane? 0. Its speed is 400, and a moment later its speed is still 400. So how much did it change? 0. All right, so I want to take a moment here to point out the common mistakes that beginning students make is they mix these up. They want to think about acceleration, but they put speed in its place. Speed and acceleration are not the same thing. I'll say it again, acceleration is how it is changing. Usually this helps with an analogy of money, because people understand money a little bit better than they understand physics. And so if you've got some money in your wallet or your purse, and you don't spend any, your change is zero. But if you had a lot of money, you still have a lot of money. So, $100 is a lot of money to me. So you have $100 and you don't spend anything, you still have $100. You still have a lot of money, but you don't have any change in your money. And so your acceleration in that case would be zero. There's no change to your money. That's that airplane, still going 400 miles an hour. Of course, you could also have the flip side of that. You could have no money. Somebody walks up to you and gives you $100. Ooh, you just changed a lot. But the amount you actually have was zero. Now, of course, once you change by a lot, then you have a lot. So your speed would be going from 0 up to 100, but your change is huge. And so don't confuse the change of your money. The change of your money is what you actually spend versus how much you actually have. And hopefully you don't spend more than you have. And so hopefully you just spend a little bit, but you have a lot, okay? And so there is an incredible difference between them that are so easy to confuse. I'll try one more here. I'll take this same number, but let's just say instead of me starting at 6, let's say I was going really fast and I was way over here and I was going 30. But I have an acceleration of a negative 5 meters per second each second. So if I'm way over here and I'm going 30, but I am accelerating. Now it's a negative acceleration. We don't like to use the word de-acceleration. We'll explain more on that in a minute, but if you want to use it, I understand, and that's fine. But what would be my speed here if I'm going 30, and then a second later, how fast would I be going? 25, because I change my speed by 5 every second. I change by 5 meters per second each second. So I would do something like this. I would start over here with 30. I would be then losing 5, so I'd be going 25. A second later, how fast am I going? 20. I change by 5 meters per second every second. A second after that, how fast am I going? 15. A second after that, 10. You see, I constantly change by 5 meters a second each second. So I hope I didn't spend too much time here, but that one I think deserves a little bit more than velocity, because I think it is very easy to confuse, and I've seen students do that. But I would say then that we are almost done here with the concept. Could we put this into a set of equations that might be useful so that if we kind of work them out now during the homework or the task, we could just kind of use those equations that we work out? So let's go to step 2. Because I think we got step 1, which is to understand the new concept. Speed, velocity, acceleration, instantaneous versus average. And so I think we got the concepts. Now let's put them into equations. Although I should do one more step before I finish here. Because if you take my whole change in speed and divide it by time, wouldn't that really be the same discussion we had where that would be the average? How would I write the instantaneous acceleration? What would I mean by that?
It would be derivative.
Right, so let me do that in 2 steps. I would first take this thought process that I want to measure how the speed changes in a short amount of time. And using the symbols from your calculus class, that would be the limit as time goes to 0. And then using that information from your calculus class, somebody out here said it, that would be then the derivative of the velocity. All right. So let me clear off the board and put in symbols everything we just been talking about for the last hour. And I will keep emphasizing, when you do a physics problems like this, you got to be doing both the concepts and the math. All right? And so now let's start applying the math to our concepts. We'll start with just some symbols here, but here's what I like to put on the board. For this last hour in this chapter, I guess we've been talking about x, the position of an object, v for velocity of the object, that's the rate at which it changes its position. And then more recently, we've been talking about the acceleration of the object, which is the rate at which its velocity changes. And what we've come up with conceptually is they're connected, aren't they? You're really saying velocity is this. You're saying it's the rate at which its position changes. And then, of course, the other thing we said is then the rate at which its velocity changes is the concept of acceleration. And so what I'm hoping to get across to you is kind of a conceptual understanding of position, velocity, and acceleration, but then how they are mathematically connected. Now, you, I suppose, will also have not just instantaneous, but also average ones. So maybe I'll put in here your average stuff. But here I have a math question for you. What if I knew it the other way around? See, I had been doing a description here of talking about position leading to velocity. See, I did this. I said, I'm going to stand here 4 meters from the wall, and I'm going to run over here until I am 12 meters from the wall. And that was my change in position. But what if I had done it the other way around, and I told you the velocities, and I wanted you to give me the position? Yeah, good. That's what I'm trying to draw out of you. What is the opposite of a derivative is a antiderivative. Another name for that is an integral. And so whether you want to call it the derivative or, the antiderivative, which is a good name here because I'm trying to emphasize that it's the opposite. I want to undo it. And so I'm going to put in this little chart, how do I go from velocity to position? What does the antiderivative look like? It's supposed to look like an S, elongated, right? That was Newton's thinking about making a summation. And so the meaning of an integral is a summation. It's also the antiderivative. That's why we got both names for it. And so if I integrate the velocity, and I'll say with respect to time, I would get position. And so how would I go from acceleration to velocity? Well, same thing. I would do this antiderivative. I'd do this integral. And so the integral of acceleration. This is my way of starting to remind you of some calculus. I think it's best to start doing some examples to show you the calculus. In fact, the first bit of calculus I will do with you, and once we do it, the good news is you don't need to do it then when you do the problems. Yay! But there are some problems where you'll see here, you got to go back and do the calculus. And that's why I've given you a few of the calculus ones. And so your homework for this chapter, you'll see most of the problems are from the college physics book, but there are a few then from the university ones. That's the ones that throw in some calculus. So the college physics one doesn't have any. So again, don't have too much math phobia here with the calculus, but we're going to do a little bit of it. okay? And let's do our first bit of calculus together. But what I want to do then is, in kind of my own silly way, would you like to know the answer to every homework problem for this chapter? There it is. I can guarantee you that if you keep this mental picture of this box in your head, they will give you one of these and ask you to find the others. And so where in this puzzle do you start? If they give you position and they ask you for velocity, take the derivative. If they give you position and they ask for acceleration, take the derivative twice. If they give you acceleration and ask for velocity, take the antiderivative once. If they give you acceleration and they ask for position, take the antiderivative twice. If they give you velocity and ask for position, take the antiderivative. But if they also ask you for acceleration, then take the derivative. And I know it's kind of silly, but I'm going to say it again. Would you like to know all the answers for all the homework problems on this chapter? There it is. This fits my strategy that I really want to get across to you, because I think physics can be a lot different than any other class you've taken. It's not a whole lot of memorization. This is it. This is the whole chapter. But I know what happens when you sit down and do the homework problems. They're not easy. But I can guarantee you it's just the deductive reasoning on that. So it's not a whole lot of memorization. Although I must admit, there is quite a bit of math in here. So why don't we do some math together and end up with some formulas that already have the calculus done for us? And for you guys, I would encourage you maybe to memorize a few of these equations where the calculus is already done, so you don't have to start back and do the calculus from scratch. And there's like 5 of them that are probably worth memorizing. I'll let you make the call. We'll do the first one. Some people only like to memorize the first 2 because, as you'll see, the other 3 are derived from the other 2. So it's kind of a judgment call here. But let's work through these together. Let's do this. Let's start with an easiest problem we could probably be given, and that is, what if the acceleration is equal to a constant value? This is fairly common. You're going to see here in a little bit, we'll do some numbers. I will put the ball on the hill and roll it down. It'll take about 4 seconds. It'll go 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000. But because of the slope of it, this gives me a constant acceleration. So this would be a good example of a constant acceleration. Now, don't get me wrong. If I gave it a higher slope, it would still be a constant, but a bigger number. And so if I put it here, you'll see it takes a lot less, well, not a lot less, somewhat less than 4 seconds. 1, 1,000, 2, 1,000, 3, 1,000, oh, and it's already off. But I want to emphasize it still is a constant. Now, you can probably even notice that if I went higher, it would be a higher constant. In fact, how high could this get? Yeah, and I would argue that it would keep getting bigger until you're essentially just dropping it straight down, which then you don't even need this anymore. So I'll just put this over there and then find the ball. Right, lost it. Uh-oh, I really did lose it. Did it go down that step? Oh, there it is, thank you. All right, and so if I just did this, that too would be a constant one. In fact, this is going to give me a chance to say that free falling is a constant acceleration. In fact, this will be the fun lab we do today. We're going to actually drop two different objects. One of them is Bob. We'll drop Bob. Bob's not a real person, but it's a plumb Bob, so we call him Bob. So we're going to drop Bob, and we're going to measure the acceleration of Bob. We're also going to drop another object. It's a little plastic, we call it a picket fence. You'll see why. But we're going to drop that one too, and we're going to measure its acceleration. And hopefully what we will see is that these falling objects have a constant acceleration, and we will know its value. You might even already been exposed to this. Anybody know the constant value of acceleration? Yeah, so it's 9.8 meters, and here we are again, meters per second each second, or you could write it as 9.8 meters per second squared. Right? Those are both valid units for the acceleration. This is a little more useful when we do the math. This is a little more useful when we think about the concept of what it is. But that's free fall. By the way, what direction is it? In fact, just asking that question, doesn't that begin to tell me that it does matter what direction it is? Which tells me acceleration is a vector, so velocity is a vector. Position is a vector, acceleration is a vector, but time, temperature, and mass are all scalars. All right, so just want to point those out. Sometimes it matters what directions, and some things don't, but acceleration does. So I'm gonna put down. Normally we put a negative for down. So a lot of people will write it as negative 9.8 meters per second squared. And nothing's wrong with that, except for you don't always have to call down negative. So if you stop calling down negative, you better stop calling that negative, because it's definitely down. Yeah.
How can the acceleration be constant? Like, how could it be 9.8 if, like, say something was heavier or lighter? Like, wouldn't it have a bigger...
I'm glad you said that. Perfect timing too, because what you are saying is very similar to what some of the early scientists thought before Galileo, and they thought, okay, well, if you take a heavier object, so I got this softball, and a lighter object, I'll take this ping pong ball, and if you drop them, they have the same acceleration, but this one's heavier? And I think that's what you're thinking. You're like, oh, this is heavier. This is going to be pulled down more. Well, as you're going to see when we get to the next chapter, it's true that this is heavier, but this also has what we call more mass, and so it's harder to make it move. So you do give it more force, but at the same time, it's all more material, so it's harder to make it move, where the lighter object has less weights, but it's easier to move because it has less mass. They end up in the same value. And so you can kind of see that. If I drop these two, I'll put the bottom at the same height thing, hit the bottom together. And so Aristotle was, arguing with what you said, that, oh yeah, the heavier one should hit the ground first. And Galileo actually then started climbing up the Tower of Pisa and started dropping things and going, no, it's not. And that was a big change in science, and that would be a fun discussion, but I better not get diverted over there. But I even brought the basketball, which is even heavier than the softball. And I think I even have something lighter than a ping pong ball. Well, no, I don't. So ping pong ball and basketball, and if I put their bottoms near the same, they'll hit at the same time. Question?
If acceleration is constant, would velocity be zero? Or would something be zero?
No, so, okay, all right. So if your acceleration, which way did you say it? Say it again. If your acceleration is constant?
Yes, then would the velocity be zero? Because it's like constant over infinity would be zero.
Well, no, so it's not infinity. It's not over infinity, right? This is a constant acceleration would mean what? In fact, maybe this would be a good time then, even before we've done the math, to jump back to this one. And roll this down the hill again. And I'm going to give you the number here. The acceleration for this is 30 meters per second each second. In fact, maybe it's worth putting here on the board so we have something to work with. So for this one, I'm going to say A is a constant acceleration. And A equals 30 centimeters per second each second. If you want to write it as 30 centimeters per second squared, that works too. But let's talk about what this means. This means it changes its speed by 30 every second. So your comment was the speed would be 0. I would say no. Maybe at one moment it's 0, but it changes by 30. So if it was 0, the next second it would be 30, and then 60, and then 90, and then 120. And that's what we have here. If we start here at the top, right when I let it go, I would say, okay, that's 0 speed right here. And 1 second later, it's here. So here's 0 speed, and a second later, it's here. So when it gets here, it is now going 30 centimeters a second.
Okay, that makes sense.
It changed by 30 in 1 second. And at number 2, it's right here. Watch. 1 1,000, 2 1,000. Right here. How fast is it going right here? 60 centimeters per second, because it changes by 30 every second. So 0, 30, 60, 90, 120. It changes by 30 every second. So constant acceleration means constantly changing your speed, right? It doesn't mean staying your speed. It means constantly changing. Now, what would 0 acceleration be, by the way? Constant speed, right? 0 acceleration means 0 change. And so if you're in a car driving down the freeway at 65 miles an hour, and a moment later you're still going 65 miles an hour, you have no change. So your acceleration is 0. Your speed is 65, but your change is 0. And you're good. I mean, and you're touching exactly what I want to have this discussion. It is that difference between velocity and acceleration that's tough to understand. Yeah.
Would you say constant acceleration was? You said that you made like a constant acceleration is like it was constant, not constant speed.
Right. So constant acceleration is not constant speed. It is a constant change to your speed. Again, maybe if it helps, we'll go back to money, where I'll equate acceleration with your hourly rate. You know, let's say I'll keep it simple, $20 an hour. So every hour, you get another $20. So you work for 1 hour, you now have $20. The next hour, you now have another 20, so that's 40. The next hour, you have another 60. So your rate is a constant. And of course, how much money you have keeps increasing. So that would be your speed. Your speed keeps increasing because you have a constant rate. Good. I'm glad you guys are seeing this, because, as I said, we should probably work out some equations. And of course, what I'm going to do for this first case, and the easiest case here, is do a constant acceleration. But I wanted to point out that if you come across a homework problem, and you will, many homework problems, where it starts off and it says you drop something, please know that they are telling you, A, it's a constant acceleration, and B, its value is 9.8 downward. Okay? They're giving that away to you without directly telling you.
Negative 9.8.
Okay, and then let's call down negative, so when we put it into our equation, we'll give it a negative. Okay? Now, I'll also point out this. We use this number so much that we like to call it G. But I also want to emphasize G does not include the negative. So the symbol we will use when we drop something is negative G. The G does not have a negative in it. Should I say that again? A G does not have a negative in it. That way you could call down positive, and sometimes people do. But I'm going to emphasize, let's not here at the beginning. There is an advantage of not calling down negative, because then you don't have to deal with negative numbers. Then there's the disadvantage of, I'm so used to calling down negative that I'm confused. And so that's the trade-off. Yeah.
So it does matter if you use the negative or not?
Oh, yeah.
And then which one was it most of the time that we used?
So most of the time, we're going to say a free-falling object has an acceleration of negative 9.8 meters per second squared. Because we're going to call down negative, and it's going to be free-falling. Now, this might also be a good time to emphasize the phrase free fall, because you guys were heading on the right path. And let me take something that's super light and see if it falls at the same rate as this softball. Not even close. But of course, the reason why is there's more going on than just gravity. This is interacting with the air. Now, I guess technically when I dropped the ping pong ball, there was an interaction or an air resistance too. But the ping pong ball was pretty small, and it wasn't going real fast, and so the interaction with the air was negligible. If I had dropped it from a tall building, that wouldn't be the case. And so when we use that phrase free fall, we're really saying without air resistance. Oh, which is why I decided to bring this out. I thought this would be clever and hopefully allow you to see it better. But if I take this tube, can you see these white pieces falling? There's a kind of a shiny disc, and then there's a white feather and a white tissue paper. And when I turn them upside down, you'll notice they don't seem to fall at the same rate. And I would say that's because they're interacting with the air. If there wasn't any air, they would fall at the 9.8. That's what we call free fall. And so that's why we have this vacuum pump out here. So I can turn this on. And suck all the air out of here. Let me check the gauge. Close the valve. And hopefully I got all the air out of here. And now let's watch them fall. There's no fluttering going on, right? They fall together. And the best I can do, they fall at the same rate together. And so this is my emphasis to all your questions, that yes, every object falls at 9.8 if it doesn't have an interaction with the air. And so there is the acceleration. Big object, small object, old object, new object, green object, blue object. Sometimes people really make physics harder than it needs to be, and they worry about, well, but when you dropped it, it was before lunch, and now it's after lunch. It doesn't matter, okay? Physics really is a few powerful, fundamental concepts that explain the universal phenomenon. But it's those few and powerful ones that then you got to reason out what's happening, and there's a lot of steps in there, and that's what makes it hard. So it's not the material itself, I don't think. Although it's kind of the concept of the material. So I'll give it that. But there's not much material. So I'll say it again. We've only done, what, speed, velocity, acceleration? And of course, you guys have a lot of questions, and rightfully so, because we're trying to figure out how all this ties together. And we still haven't done the equations yet, but we're going to, I promise. Yeah.
So before calculus, since calculus is so important with like velocity, acceleration, before calculus, was there really much thought with physics? Was it like...
There was, but it was very limited. In fact, I would put it the other way around. The reason Newton developed calculus is because he found he couldn't do any more physics without calculus. Exactly. And so calculus was not just discovered as an academic discipline and humans asking the next question. And I guess they were from a science, but not a math question. It was Newton who was looking at the motions before him, which was Galileo, and looking at the motion of the planets and looking at Galileo and said, I'm kind of limited in what I could do because I really need to take this quotient where the time goes to 0, and the math says I can't do that. And so Newton asked, well, what can I do? And so Newton invents calculus. And once he invents calculus, the amount of physics just blossoms under him. And it's because of, well, his brilliance also, but because he was able to see that physics was being limited because of the lack of calculus. And once he invents calculus, boom. In fact, there's some negative criticism about Newton because after he does discover calculus and the power of it, he doesn't share it with anybody. He kind of hoards it to himself and makes many great discoveries, but he never shares with the rest of the world calculus. Eventually, Leibniz comes around, and then that's where the controversy comes in. Who should get credit? Because Newton may have done it first, but he didn't follow the scientific lead of sharing it for humanity. And anyways, but that's a fun history there too. So I'll put the air back in here, and you'll see the interaction with the air once I open it up. See, and there can be an interaction. So once we include the interaction of air, it gets more complicated. So we'll wait till chapter 5 for that. This is hard enough with just free fall. So I'll say it again. What I want to look at is a special case of these when you have constant acceleration. But even though I say it's a special case, there's a lot of cases of constant acceleration. Free fall is just one of them. Okay, so anytime you have a constant acceleration, then let's see what that does. So let's start with this condition, if. If acceleration is a constant. All right, so I was joking, but also half serious. You want to know the answer to all the homework problems? They're right here. So let's start here. Let's start here that says acceleration is a constant. Could you give me an equation for velocity? And as you already told me, take the antiderivative. All right. So velocity would be the integration of acceleration with time. Okay. Now, let me remind you of a little bit of calculus in case you've forgotten. What can you do with constants? Do you remember that step? Constants can come out in front of the antiderivative. So it's that step right there where I'm going to emphasize everything I do from here forward is only valid if what? Constant acceleration. So for you guys, for the beginning student, it makes sense that 90% of our problems are going to be constant acceleration. Okay? So I'm going to encourage you to start a problem and ask yourself, is this a constant acceleration problem? Because if it is not, you need to do this integral on your own. If it is, then everything I'm about to do for you, you can use because of that step right there. So that's important to keep in mind. Everything we're about to do is only going to work if you have constant acceleration. But we do 95% of our problems. Okay? And free fall is one of those examples. All right. Now, I'm going to remind you of your math. Hopefully this is an easy integral. What is the integral of dt?
T.
Just t. And then, of course, what else do you do when you do an antiderivative? Plus c. And what do you mean by c? Okay, so it is some constant, and that's probably how you learned it in your math class, but I'm going to take that one step further. Let's read this math for a moment and see what that constant would mean. So we don't have to just say, oh, some random constant. It probably has a physical meaning. All right, so do you see anything what this might mean? So what if t was 0? That would go away, right? So this constant would be the speed. So what you're really saying is this constant is the speed at time equal to 0. So yeah, why don't we just call that the initial speed of it? And why don't we give it a symbol that makes it look better than this symbol? And so why don't we call this v naught? And so I'm going to refer to this as equation number 1. Very useful. I would encourage you to memorize it. It's much better than having to go through these steps of calculus, but I don't think they're overwhelming. But likewise, I don't think it's overwhelming to memorize this one equation. So here's a nice equation that relates velocity, acceleration, and time, but it can only be used if what? If a is a constant. So why don't I come over here and I'll just put it right under this box and say v equals v naught plus at. Ta-da! I'll even call this equation 1. We often refer to this as kinematics equation number 1. But I need to say it again, it would only be valid if if you have constant acceleration, but also I'll remind you, you have constant acceleration 95% of the time. Okay? And it's about time for our break, but maybe I'll do one more step and then we'll break. And as we come back and do examples, watch me when I do them. The first thing I'll ask after I read the problem is, do I have constant acceleration? Because like I said, if I do, I can use this equation. If I don't, I got to come back here and do my calculus. And fortunately, 95% of the time, I don't have to come back and do my calculus. But 5% of the time, I do. Now, let me take the next step here, because you saw this in the chart right here. Could I get an equation for position? Yeah, if I do what? Integrate velocity. So let's give that a try. So this says I get an equation for position if I integrate velocity. All right, again, for a lot of you, it might have been a while since you've done your calculus. Could you help me with this integral?
It's the same idea, you pull out v.
Okay, can I pull out the v? Yeah, let's go back here. I can pull out the a because it's a constant. If v was a constant, I can pull it out. But it is not. How do I know that? Well, I just argued that v would follow this equation. In fact, to remind you of some more math, isn't this the equation of a line? If I plotted t on the x-axis and velocity on the y-axis, wouldn't this be the intercept? And that would be a line, and that would be the slope? This is going to help you today in lab. That's what we're going to do. We're going to measure the velocity of Bob. We're going to measure the velocity as a function of time. We're going to get the slope, and that's how we're going to get the acceleration for Bob. So that's what this math is saying. Oh, good. I get to use that phrase again. Read the math, right? What is this saying? Okay, so this is saying the velocity does change with time in a linear fashion. So can I pull out the v? No, but I could do this. I could put this equation in there. So this says v naught plus at dt. Ah, that would be my next step. Now again, maybe I'll help you with a little bit of calculus. When you do an antiderivative, you can break it into the two pieces. So this would be in the integral of v naught dt, and then the other integral would be at dt. All right, let's work through this one. and help me out, because it's been a while since I've done my calculus, so I need your help. What do I do with this? Good. A couple of you sounded like said it. That's just a number, right? That's a constant. That can be pulled out in front. So this step is really kind of the same as that one. In fact, if you let me do two steps, if I pull this out in front, then I just have the integral of dt, which is what? Yeah, it's back to this. That's just a t. So I would say that this right here is just v naught t. Good. Now let's look at the second one. There's that a again. What can I do with that a? Pull it out, right? Again, that's the condition. This is only going to work if we have constant accelerations. And so I'm going to pull that out. And so this would be an a, and I'd have an integral of t dt. Ooh. Maybe this needs a little calculus review. In your calculus, you probably saw it like this. What's the integral of x raised to the n power dx?
Is it going to be xn plus 1?
So you raise the exponent by 1 and divide by that new exponent. All right. Keep that in mind, because we won't do any integrals harder than this. This is it. Our integrals will be power functions. So those of you who've been a while since you've done calculus, or I know some of you online have, you're actually struggling through the calculus right now. Okay, and the calculus we will do, this is the hardest thing. Okay, and the reverse of this, the derivative. So these are called power functions. Okay, so when you have a power function, you just raise it by 1 and divide by that new exponent. Now, technically, I actually did that back here, but it was so easy I didn't mention it, because technically this was t to the 0 power. So then I became t to the 1 power divided by 1. This one's a little more advanced. What would this become then? So this would become t squared over 2. Now, I'm going to say it again in case I didn't get this clear. You don't need to do this calculus if you have constant acceleration. That's why I'm doing it for you. Okay? This is going to be equation number 2. Memorize it. Okay? However, you talking about a constant run? Yeah, thank you. Thank you. I haven't forgotten that one. I'm getting back to it. But what I wanted to emphasize to you guys is right here that this will be good. Well, I still have more to do. I got the constant. But we still have 95% of our problems are going to use this. The 5% where we can't use it, we're going to have to actually do our integrals. But what I'm trying to say, of all of those 5%, this is the kind of integral you will do. Okay? You will do a power function. So if that helps anybody who's a little worried about their calculus, this is not meant to be a strong calculus class. It's meant to be a strong physics class and use some calculus along the way. Okay, now, I will point out, as some of you already noticed, is don't forget, like we said over here, you have to have a constant. If it'll be okay with you, I'm not going to put 2 constants. I know technically I did 2 integrals, so shouldn't there be a constant for each of them? But if they're a constant, couldn't you just add that together and call it 1 constant? All right, so that's what I'm going to do. I'm just going to say, look, there's some value that is a constant that is really the sum of the 2 constants that go to it, but I'm going to ask you to go one step further than you did in your math class. Just like back here, don't call it a constant. Let's study the math and see what we can call it to give it some usefulness. Let's do that here. So if this equals the position, could you study this, look at the math, give me a chance to say it again, read the math, and tell me what this constant would mean to you? See, right, when time is equal to 0, that is 0 and that is 0. So when time is 0, this constant is the position. So this constant must be the position when time is 0. So let's call that x naught. So if we call that x naught, we end up with what I'm going to refer to as equation number 2. The position is the initial position times the initial velocity multiplied by time, then 1/2 at squared. And that's how we went by given acceleration. We could integrate once to get an equation for velocity, integrate a second time to get an equation for position. And so that's our 2 kinematic equations. Now we can manipulate these 2 and come up with 3 others, and we will do that after the break and then start to use them, but now is a really good time for a break. You guys have been slugging along really well here, so time for a break here. So let's take a 15-minute break and come back. Yeah, you can, I guess, stop it, Ron, and then we'll changing the conceptual fill into math and then actually doing them, and seeing somebody do them is really the best way to get yourself ready for you to do them yourself. All right, so that's where I really want to go here, and we will begin by pointing out that so far we have gotten 2 equations. We refer to these as kinematics equation number 1 and number 2. Okay, let's put them into action. If you remember, we had this little incline where I said this is a constant acceleration problem. And if you remember, we did it conceptually. We said what would be the speed when it got down here after 4 seconds, right? We went 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000. And we said the acceleration was 30 centimeters per second each second. So here it is going 0, then 30, 60, 90, 120. So after 4 seconds, it should be going 120. And we did that conceptually. Let's do it mathematically now. Let's try to apply equation number 1. So if equation number 1, or the question says, after 4 seconds, given this constant acceleration, starting from rest, how fast is it going? Now, I want to show you a little pattern here. Well, let me say that again. Constant acceleration of 30 centimeters per second each second. So they gave you acceleration. After 4 seconds, so they gave you time. Starting from rest, so they gave you initial velocity. And they're asking for final velocity. Did you notice they never said in that problem that I'm making up about position? See, here's what I want to emphasize. The reason I decided to do this problem and using this equation is I'm going to focus on what is not in that equation. So I'm going to put here not an x or an x naught, which maybe we should put them together. What's a good way to write this? Not x, x naught. But remember, delta x is how far it travels, which is the 2 together. But what I want to overemphasize here is thinking about which equation would be useful. I see that equation number 1 has 4 variables in it, and I could solve that equation for any of those 4. But I could never solve it for position. So if they're asking for position, equation number 1 is a mistake. Get that? But also, if they're not giving me position in the problem, then that's also probably the reason I want to use number 1, because I don't know that variable. Any other equation, I need to know it, and I don't know it. And so what I'm trying to lay out here is a strategy of what equation should I use. And you're going to see that there are 5 variables here. And we're going to come up with 5 equations. And each of those equations will be missing 1 variable. And so when you get a problem, focus first on, number 1, is it constant acceleration? Okay. Then if it is, focus on what parameter did they not give you and they're not looking for you to solve for? Because if they're not asking you to solve for it, you don't need it in that equation. And if they haven't given it to you, you don't want it in the equation because you don't know what it is. All right, so in this problem, I'm telling you the acceleration, I'm telling you 4 seconds, I'm telling you the initial speed, I'm asking for the final speed, the thing missing is position, and that's why I would do equation number 1. And so I would walk up here and say, all right, I can do equation number 1 and say its initial velocity is 0 centimeters per second. Its acceleration is 30 centimeters per second squared. And 4 seconds later, what do I get? And if we do the numbers, 4 times 3 is a 12 with a 0. There's the 120. One of the seconds cancels with one of the seconds, and I get 120 centimeters per second. So there it is. We did the same number conceptually. We get the same thing mathematically. How about I ask this? How far did it go after 3 seconds? Okay, so I know the acceleration. I'm telling you after 3 seconds, so there's the time. I'm going to release it still from rest, so I know initial speed. In other words, what is it I don't know when I ask that? When I ask you, how far has it gone after 3 seconds? Okay, so what's missing is velocity, isn't it? Now, not the x. The x is how can I say this? The x isn't missing from my statement. I'm trying to find that. So that's part of the problem. My x is part of the problem. So I want to make sure my x is part of my equation. Okay? So I don't know what it is, but I'm trying to find it. So it needs to be part of my equation. I'm telling you 3 seconds, so time needs to be part of that equation. We know the acceleration. That needs to be part of the equation. I know the initial speed because I say I released it from rest. And what I'm trying to get you to see is if you study all the things that are given to you, you will recognize that what is not known is the speed at 3 seconds. Now, that doesn't mean we can't figure it out. But what equation should I use would be the equation that is missing final speed. And as you're pointing out, number 2, right? And so number 2 right here does not have the final speed. So if you are ever giving a problem that, first of all, has constant acceleration, that's a must, but they don't tell you the final speed, and they don't ask for the final speed, equation number 2 is your go-to. That's what I'm trying to point out. And that's what I'm going to do right here. I'm going to say how far did it go in 3 seconds, and I'm going to use equation number 2. So equation number 2 would be x equals to x naught plus v naught t plus 1/2 at squared. And now I can put in my numbers. Now this goes to what we started at the beginning of the lecture. Remember, we could call 0 anywhere we want. So why don't we put x equals to 0 where we started it? And I would encourage that unless there's a reason to do otherwise. All right, so I'm going to say it starts here, and so after 3 seconds, 2, 1,000, 3, 1,000 right here. I'm going to say, how far is that? So I'm going to put here a 0 for the initial position. Remember, I released it from rest, so there is the initial speed of 0. And then I'm going to have a 1/2. Then I'm going to have 30 centimeters per second squared. And then I'll have 3 seconds squared. And as I do the math, you'll see here that, of course, 3 squared is a 9. 9 times a 3 is a 27. Half of 27 is 30. Half of 27 is 13.5. Oh, and then a 0. So 135. Seconds squared would cancel with seconds squared. And so it'd be 135 centimeters. So that should be its position. Okay. Now let's play a little more mathematical trick. What if they said something like this? What position is it as it rolls down when its velocity is 100? Now, I'm going to ask again. Think about mostly what is not given. All right, so they're asking for the velocity. I do know the initial velocity. I know the acceleration, right? They're asking for, no, I gave velocity. They're asking for position. What's missing? What variable? So we've got initial velocity, we've got final velocity, we've got acceleration, we've got time. Oh, which one did I miss? Position? Position. Did I say position? So there's 5 up here. There's initial velocity, there's final velocity, there's acceleration, there's time, and then there's position. And actually, I'm going to treat this as one variable because this would be an x minus an x naught. Okay. What I was trying to say is that particular problem is asking for at what position is it when it has a speed of time was never there. I don't know what the time is and I'm not asked for it. It would be nice if I had an equation that didn't have time in it. Let's make one. It's pretty easy to do. And this is where it's going to have to be a judgment call on your part. Some people like to memorize the next equation. Other ones say, what a waste of my time, because what I'm going to do is solve this for time and put it into here. So if you want to do that, go ahead. Because that's exactly what I'm going to do. I'm going to do the 2 steps for you. And so if you memorize this third equation I'm about to do, just remember that you don't have to do the 2 steps. I'm going to reduce it down to 1 step. And so if you don't mind memorizing another equation, it'll save you a step. However, if you don't prefer to memorize the equation, just remember you got to do 2 steps. So it's your call. But we could keep doing this forever and ever, and we would have so many equations to memorize, it would overwhelm you. And then that misses the point. I don't want you to memorize a bunch of equations. That's not what physics is about. Physics is about working out the logic for it. Because I'll say it again. Didn't these 2 equations actually come from this? So if you just want to do a very little memorization, just this will get you through the whole chapter. However, I would suggest you at least memorize these 2, because these 2, you got to go through a couple steps of calculus like we did. Now, the third equation, I'll put it over here, equation number 3, is very useful, because watch what happens if I solve this first one for time. So I'm going to come over here and take velocity equals initial velocity acceleration for time, subtract the initial velocity, divide by a, and now I have an equation for time. I'm going to take this, so this is equation number 1, and I'm going to put this into equation number 2. Now, it does take a little bit of algebra, so let me kind of work through the algebra here with you. But if I put for time v minus v naught over a, and then over here I put 1/2 a, and then I put v minus v naught over a squared, I can simplify all of this. It is quite a bit of algebra. That's why I encourage students to memorize this so you don't have to do the 2 steps, but it's your choice. I just want to emphasize the equation I'm about to come up with does not have time in it, and that would be the equation to use when a problem is not asking for time and doesn't give it, because it's been eliminated. That's why I solved equation 1 for time and put it into number 2. Time is not part of this. All right, so let's simplify this a little bit. I will start by moving x naught to this side so that those are kind of grouped together. I'll think of those as one variable. How far did it go? And that's kind of my question. Where is it? How far does it go when it's going at a speed of 100? Okay. Then I'll multiply these out, so this will be V naught times V over A, and this will then be V naught squared over A. This is going to take a little more work because it's squared. I'll start at the bottom, so this will give me an A squared at the bottom, and then this is going to take us back to our algebra class, right? A minus B squared is A squared minus 2AB plus B squared. All right, so the first one squared, that's the A squared, minus 2AB plus B squared. Now, I'll do another line here. I'll leave these two alone. Maybe I'll do a little bit and do a 1/2 and then 1 over A. Actually, if you'll let me, I'll put this up here. 1/2 over 1 over A. So I'll erase that. And then let me multiply this out. So this is going to be then V squared over 2A. This will be minus, and then I'll get a V naught over A. Notice how that 2 and that 1/2 cancels. And then this is plus then a V naught squared over 2A. And then notice that this term and this term are equal and opposite, so they'll go away. Notice that this second term and this last term are like variables, although this has a 2 downstairs and that does not. So I'm going to write this third one first, and then put these two together. So this is a plus 1/2, but this is a minus 1. So that'll leave me with minus 1/2 V naught squared over A. Notice that each of those have a 2A in the denominator. So then we get V squared over V naught. Fractions are never fun to memorize, so let me move it to the other side. So 2A x minus x naught equals final speed over initial speed. And we like to then put the initial speed on the other side of the equation. So we have then what we call kinematics equation number 3. And I will put it right here, that says the final speed squared equals the initial speed squared plus 2 times the acceleration times the distance traveled. What I want to emphasize, like in these other ones, is when would I use that? Well, what variable is missing? Time, not time. So if you ever have a problem where time is not given and is not being looked for, got to keep both of those in mind. It's not given and you're not being asked to solve for it. You would want to use the equation for that. And this would be a perfect one for that. In fact, let me use it for that problem I described. The problem I was describing is, could you tell me how far down it goes when it has a speed of 100? So, using this equation number 3, I would put 100 centimeters per second and square it for the speed that it's telling me about. I would then put in the initial speed. So remember, we're starting up at the top, so the initial speed would be 0. I then would put in the 2 and the acceleration as 30 centimeters per second squared. And then this would be what we are asked to find. How far did it go? Okay. Now, maybe I'll start with the units, because centimeters squared on this side with a centimeter means one of them will cancel, and on this side you'll be left with centimeters. Downstairs, you will have seconds squared, which would cancel with the second squared on that side, which is great because we want the units to come out to be centimeters. Remember our unit analysis we talked about last time? We are asking a question, how far did it go? The units need to be centimeters or millimeters or meters or something like that. And if our units don't come out to be that, we've done something wrong. And so take advantage of the unit analysis. And so now I'm feeling good. Maybe I'm on the right path. The units are working right. Okay, good. And of course, then what I have is 100 squared, so that's 10,000. And then number-wise, 2 times 30 is a 60, and I'll bring it over here, so that's a 60. And so grabbing my calculator, 100 squared divided by 60 gives me a position of 167 centimeters is where it would be having a speed of 100. Which, I don't know, somewhere around here-ish. Okay. Well, let's keep going. Because we can play the same game and call it equation number 4. We could have a problem that doesn't give us the acceleration, and we're not asked to find it. However, I should emphasize on this one that if they do that, they do need to say it's constant acceleration, because remember, these equations are only valid for constant acceleration. So if they don't give us its value, they at least have to give us a clue that it's constant so I can actually use this equation. Okay? But can I play the same game? Why don't I just solve this first one for A, put it into here, and we have an equation that doesn't have an A for it. And so this would be the perfect equation to use if you do not have A and you're not looking for A. And let's play the same game one last time and solve it for initial velocity. And say if they ever give us a problem where they don't tell us the initial velocity and they're not looking for the initial velocity, we would use that equation. And we're going to do the same thing. We're going to solve this one for initial velocity and put it into here. So that's why I was saying equation 3, 4, and 5, you really don't need to memorize. Equation 3, 4, and 5 are really the 2 steps. Solve it for whatever variable and put it into here. Whichever one's missing, put it in here. So you can just focus on these 2 if you want, or you can learn all these 5. Your choice. Personally, I would encourage you to have all 5 written out on a note card because the test is open notes and they're sitting right there. And so when you take the test, you're just going to go, perfect. There it is. There's the one I want. Okay. All right, so let's give you this equation. Okay, so let me play the same game. Let me solve the first equation, and maybe I'll do this a little faster so we can get into some problems. If I take the speed or the initial speed, take the final speed, subtract the initial speed, divide by t, I'm going to get A. So this is solving equation number 1 kind of quickly for A, and let me put it into number 2. So putting it into equation number 2, I would have x minus x naught equals v naught t plus 1/2. So I'm going to just go ahead and take equation 2 and move the x naught to this side already. I'm going to take the acceleration and go v minus v naught over t for the acceleration. That's up there from equation 1. And then I'm going to put a t squared. And so x minus x naught. And as you'll see, I have a v naught t, and right here, one of the t's cancel off. And so if you do the distributed property here, you're going to get a vt over 2, and you're going to get a v naught t over 2. You'll also see this first term and last term are the same. although this is a plus 1 and that's a minus 1/2. So when you put those two together, you're going to get a plus 1/2 v naught t. That looks funny. How about that? And then, of course, this is Vt over 2. And if we simplify it, which I think makes it a little bit easier to memorize, we'll factor out the 1/2. We'll also factor out the t. And so we have a nice equation that says how far does something travel is equal to 1/2 times the speeds added together, final and initial, multiplied by time. In fact, it's even easier to remember it if you do this, because this is probably how you learned it in like a 7th grade physical science class. This would be your average speed. How do you average two numbers? Don't you add them together and divide by 2? So average speed multiplied by time is the distance traveled. Velocity times time is distance traveled. And so that's how I remember it, to say, hey, it's average speed multiplied by time. And the average is beginning and end, divide by 2. That's how I get an average. But I want to emphasize is notice that this equation does not have an a in it. So when I read a problem, I'm going to ask myself, are they missing a? And they're not asking for a? That's the go-to one. Now the last one, it would be to then solve this equation, number 1, for initial velocity. And so I would take final velocity and subtract AT. I think that's what I got. If you let me go a little quick here. And so I got initial velocity, and I'm going to move the AT to the other side. So that is final velocity. So I'll call that equation 1. And then I'm going to jump down here into equation 2. And in equation 2, right here, or right here, I'm going to... Oh, sorry, I bumped it. Sound still good? I'm going to put it right there. Okay? And so I'm going to put V minus AT times T, and then plus 1/2 AT squared. And so if I work this out, this first one is VT. This next one is minus AT squared. This next one is 1/2 AT squared. And notice how the second and the third one are like terms. So this is going to be final speed multiplied by T. This is then a negative 1/2, because this is a negative 1 and a plus 1/2 T squared. And that's probably the best way to write that one. And so I'll put this one over here, which says here equals VT minus 1/2 AT squared. And like I said earlier, I think the best way then to really show you this in action instead of doing a bunch of symbols is, hey, let's open up the book. Let's read some examples. Let's see how far we can get. We still have, 25 minutes here to do some good ones and some hopefully some challenging ones here. And let's see which problem to use and how we might go about solving these problems. Okay, so turning to your book, and in this case I'll pull down the screen and say, all right, let me turn this display on. Let me come over here and go to the end of, oh, how come you're not responding? There we go. End of chapter 2. Let me kind of scroll up here to the problems. Maybe I will, let's see, do this. Maybe that's a good way to do it so you guys can see it. And let me just go through my list here. And I thought there was a bunch of problems that looked really good. I'll start with number 21. And like I said, my goal here is really kind of just train your thinking. Now that hopefully you put all this together. Remember, here's how we started this chapter, right? A new thought. And so we got speed, velocity, acceleration. What are those differences? We changed those thoughts into equations, and now we've worked out a lot of equations. And so it may sound like we've done a lot, but I want to emphasize, do you want to know the answer to all the homework problems? There it is. It's in the blue box. And you can always start here and do all of them. Although I would suggest that if you have constant acceleration, since we already did the antiderivative, you at least memorize these two. And if you want to go a step further, maybe it's worth memorizing step 3. Maybe even 4 and 5. Okay. I will point out that your author, what page is it? Page 57, gives you a slightly different set of 5 equations. I'll let you make the call. I think these are a better 5 than the author. But remember, they're all just derived from each other. So this is what I prefer as the 5. I know that I've had a lot of students who prefer just these 2. So again, that may be some of you just going, well, didn't those 3 come from these 2? Yeah. I would say even the second one came from the first one by doing an antiderivative. The first one came from here. So where do you draw the line? I will draw the line at 5, though. If you start trying to memorize more than 5 equations, you'll be overwhelmed. You'll get to the final exam and go, I can't remember all these, although it is open notes, so maybe you can just add it to your note cards here. But you're kind of missing the main point here of physics. I'm trying to say it's just a few fundamental principles that explain a universe of phenomena. So just knowing the concept of what is speed, velocity, and acceleration, and how they're related by the derivative, that stuff in that blue box, you can do all these motions problems. You don't even need those 5 equations. And 5 is just, to me, kind of a happy medium where I don't have to rederive everything, but I don't have to memorize too much. All right, so I'm going to try number 21 here and say, all right, let's read it together. Let's think about it. And I'm going to hopefully point out that the very first question I'll ask myself is this a constant acceleration problem? Now, maybe I should even backtrack a little bit, because by the time we get to, say, the final exam, you might want to start asking yourself, is this a kinematics problem? Because we'll have other problems involving momentum and energy. But since we're just at the beginning, we already know it's going to be a kinematics problem. So we don't have to ask that. But it may be a good point for me to start there. Okay, so yes, this is a kinematics problem. And then, is it a constant acceleration one? All right, so 21 simply says this: a well-thrown ball is caught in a well-padded mitt. If the d-acceleration, interesting, he uses the word, of a ball is 2.10 times 10 to the minus 4 meters per second squared and 1.85 milliseconds, and then they give us elapses from the time the ball first touches the mitt until it stops, what was the initial speed of the ball? Now, I must admit, the author didn't do a good job here on emphasizing that this is going to slow down with a constant acceleration. However, the reason I have you guys doing 2 textbooks is this first one doesn't do any calculus. So we know just by the nature of the book, they're going to give us a constant acceleration problem. We can't do a non-constant acceleration without any calculus. So that's kind of a cop-out, but maybe the author's trying to say, what's the average acceleration? So let's just treat this as the ball's hitting the glove and it's going to have a constant acceleration. All right, so keep in mind then that I would say, yes, this is a constant acceleration, but we don't know what it is. And we're asked to find the velocity. Well, there's my clue. I don't know what the acceleration is, and they're not asking for it. That sounds like a good recipe for...
Isn't deceleration just negative?
Oh, I'm sorry. I apologize. I said that all wrong. They totally gave us the acceleration. Sorry. Oh, and sorry, I don't even know what I was thinking. Not only did they give it to us, But notice they gave it as just a number like it is a constant. So my apologies. That's not what I meant to say. They gave us the acceleration. They gave us the time. They asked for the final speed. I was thinking of another problem. I got to rethink about this one. Is it distance they don't give us? Yeah, so it's distance they haven't given us, and it's distance they're not looking for. All right. So that would make me want to come over to number 1. And so I would say V equals V naught A T. I'm really sorry. But I feel better, though, because the author now really has given us a constant acceleration. He gave us a number. That this is the acceleration. Okay, now we are asked for what was the initial velocity. So here's what we want to solve for. Why don't I put in the things that I know? And there is a tricky one, and I'm glad you guys already saw it. What's the acceleration? What should I put in here? And it's the negative. Good. You see that. So they didn't put the negative here, but they did say it was, clearly they explained it as slowing down. They did put a deceleration. And so this is this 2.1, was it 10? Times 10 to the 4 meters per second squared. And they're going to make you recognize that it needs to be a negative. That might be the hardest step of this one. Okay. They did tell us the elapsed time. They tell us it is 1.85 milliseconds. And another kind of hard one, I don't think it's hard as that negative, but also kind of hard in here, is what's the final speed? 0. And so let me take this as a moment to emphasize that to do physics well, you got to have that physical picture. Picture what's going on. Somebody's catching the ball, and what happens after they catch the ball? It stops at 0 speed. Now, maybe after that, they throw it back or something, but they're going to catch it. And it's during that contact in the mitt that they're talking about. And so they're indirectly giving you final speed. And you have to mentally picture that in order to solve this problem. So I think the big 3 things are right here. Which equation to use? Recognizing how the negative of the math has to go with the description of a deceleration. And also recognizing the physics that it comes to a stop. Other than that, it's easy to solve the math. And maybe I'll start with the units, because a second here and a second there would cancel, and I will move this to the other side, so this will be meters per second. The negative will now become a positive. And so now I can take the 2.1 times 10 to the 4 and multiply it by the 1.85 times 10 to the negative 3 and come up with 38, and let's do our significant figures. 3 here, 3 here, should be 3 in the answer. And so that will round up to a 9, and 38.9 meters per second would be final speed. All right, should we try another one? All right, so number 27, kind of those same thoughts. And hopefully I won't confuse it. Let me read it more careful. I was thinking of another problem. So what does 27 say? 27 says a slap shot, a hockey player accelerates the puck from 8 meters per second to 40 meters per second in the same direction. Good, I'm glad they say the same direction, because that's all we're doing in this chapter. Right, one direction, one dimensional. Okay, in the same direction. if the shot takes this long, calculate the distance over which the puck is accelerating. Okay? And so I guess got to know a little bit of the mental picture about hockey, which I'm probably the wrong person to ask about hockey here, but anyways, here's a puck. And what you're going to do is you're going to slap it with your stick, and so during that time there's an acceleration. Now once it leaves your stick, you're not pushing it anymore. So they're talking about only during the slapping of the puck. There is this acceleration. Okay? And it changes its speed from a kind of a low speed to a really high speed. Okay, so and then the shot's taken off somewhere. So they're not talking about that part of it. They're talking about during the accelerating, during the time the puck is touching the stick. Okay? And so then it says calculate the distance. All right, so we got initial speed, we got final speed, we got time, we're looking for distance. It seems like we're missing acceleration. And coming over to here, the one that jumps to my mind right away then is number 4. Number 4 was deliberately set up not to have acceleration in. Now, of course, don't get me wrong, you could go back, like I said, and use equation 1 to find the acceleration and then plug it into number 2. But that's how we got number 4. So that's why number 4 is kind of an easier step to do. And so the distance traveled is then average speed multiplied by time. All right, so the initial speed is 8 meters per second. The final speed is, was it 40? 40 meters per second. By the way, notice same direction tells me that I'll call that direction positive, so they're both positive. Had they said the other direction, I might have put this as an 8 and this as a minus 40. Okay, but they didn't say it. They said same direction. Okay, then calculate the distance. Oh, and here's the time, 3.33 times 10 to the minus 2. So 3.33 times 10 to the minus 2 seconds. Okay, and so grabbing my calculator, let's see what that distance is. In fact, this is 48 cut in half. That's a 24, so my average speed is 24 meters per second. And then I will go 3.33 times 10 to the negative 2. And I will get a distance of 0 points. And let me just count significant figures. I've got 3 here, and I don't think I wrote it like they did. I should have. But they've got 3 significant figures for the 8. They got 3 for the 40. In fact, I guess when I add that, that would be 48.0, because then I wouldn't include that one, same precision. But anyway, that's 3 significant figures. Then multiply by that 3. So the answer should have 3. And so this would be 0.799. And looking at my units, the seconds would cancel off with that one, and meters. And so this is kind of this. Whew, there's my shot. And so from there to there. Sorry. As I flicked it in. And so is that what you see in your mind when you read that description? And that's the skill I want you to develop. Do you see the physical picture? It helps a lot. All right. Try another one. And let's try 49. And I'll kind of comment the same thing. And then maybe we should move into some calculus 1. But 49 hopefully is kind of that same thing that I'm going to ask, is this a constant acceleration problem? And I can pretty much answer that by saying, yeah, it wouldn't be in this book if it wasn't here. But 49 says, you throw a ball straight up with an initial velocity of 15. Ooh, this one gets a little harder. It passes a tree branch on the way up at a height of 7 meters. How much additional time will pass before the ball passes the tree branch again on its way down? Ooh, I like this one, although it is 2 steps. Shoot. And in our time frame, I'm going to change gears here. This would be a good problem too, and it's a hard problem because we've got to do these 2 times. We got to do it first from the initial movement up to 7, and then from 7 on back down to 7. And I do want to show you that. Maybe I'll make a video out of that, but I also want to show you some calculus one. And if I spend our last 7 minutes on that one, I'm not going to get a chance to jump over to the calculus one. So I want to jump over here to the calculus. And let's see. What number did I put up there? 79? Let me try from the calculus book, number 79 here. Okay. Let's do this one in our last time together. So 79 says, between t equals 0 and t naught, a rocket moves straight forward with an acceleration given by, let me just write down this equation. So the acceleration as a function of time is given by some number a, they don't say exactly what it is, minus b t to the 1/2 power. My first question for you would be, well, actually, let me keep reading it, where a and b are just some constants. So we don't actually know what they are, so we can't actually get a number out of this, but we know they're constants. Is this a constant acceleration problem? Yeah, good. You guys are shaking your head no. Absolutely not. How do I know that? Right. I have a function. It changes with time. That's what a function does. So this, you know, if you put in time equals to 0, the acceleration would be a. But then if you put in a time of equal to, say, 1 raised to 1/2 power is 1, your acceleration would be a minus b. So this little part of the function means the acceleration keeps changing. So could I use equation 5? 4, 3, 2, 1? No, none of these. I got to do this. So I need to come all the way back to my calculus in order to do this one. I don't have a constant acceleration. Okay. A. If x is in meters and t is in seconds, what are the units for a and b? Okay. So when we work with units, we like to sometimes put these big square brackets to say, I'm not talking about the equation, I'm just talking about the units. So what do we measure? What units are used to measure acceleration? Meters per second squared. And here's what that tells me. That tells me that when I add things, don't they have to be the same units? So like, you know, seconds added to seconds works. But seconds added to meters doesn't. They got to be the same units. So this must have units of meters per second, and this must have units of meters per second. So that tells me the first part of this, what are the units that go with the capital A? Meters per second squared. Now remember, meters per second would be this whole thing. So let me just look at the units of the whole thing, knowing that it must be the units of B multiplied by the units of time to the 1/2 power. So this would be seconds to the 1/2 power. So the units of B, if I bring this over to here, must be meters per second. And this is kind of weird, but I guess to the 2.5 power. And it's kind of a weird unit. Makes you wonder if it's really a valid equation. But it is a good one for a rocket, actually. They might even have said that. Yeah, a rocket moves. So it's a very common acceleration problem for a rocket. So the units are a bit complicated, and I think that's why the author wanted to ask that at first. Okay, so there's the unit of it. It says, now, if the rocket starts from rest, how does the velocity vary with time? All right. So coming back to this box, they're asking me to find velocity, right? They gave me acceleration, right? So how do I get to velocity from acceleration? Antiderivative. It's the same thing we did right here with saying 1, except when we did this one, we said a was a constant and we pulled it out. We don't get that chance. So let's try our calculus again, this time a little harder, because we can't pull out the constant. But it is just a power function, and that's what I was saying earlier, that I won't give you any problem that's calculus-wise harder than a power function. So I'm going to put here, and I'll put number 79, and I'm going to put velocity then is what you get when you integrate the acceleration. Like I said, if a was a constant, as we did before, I would just pull it out. It's not here. I've got to put in capital A minus b t to the 1/2. And then I have to separate into 2 pieces. Because we are subtracting those 2. Fancy word we learned in our calculus was this is a linear operator, so we can separate them into their 2. Then this first one, they said a is a constant, the capital A. So I can pull it out in front. And then I would just have the integral of dt, which is, remind me again, t. Good. And for the second term, b is a constant, so I can pull it out. And now I have an integral raised to a power of 1/2. How do we do an integral with power function again? What do we do with the exponent? Add 1. So this would be t. See, we already have a 1/2, and if you add 1, what do you get? 3/2. Okay, 3/2, or 1/2. Okay, I'll write it as 3/2. Good. And then you divide by what? The new exponent, which would be 3/2. And then you also do what? There would be some kind of constant that you should not stop, like you might have done in a math class, and just call it a constant. Step back and read what you've just done and give it a symbol. I think you can see it saying the velocity equals all this. What would happen if t equals 0? That would be gone, and you would get just that constant. So a good interpretation for that constant is to say, this is the speed when time is 0. So let's call that v0. Did this problem tell us the velocity started at 0 or not? The rocket, there it is. The rocket starts from rest. So not only do I have to realize that it's a 0, that it's initial velocity, but now I know it's 0. So that's even nicer. That goes away. And so the equation for the velocity becomes this. And we should probably simplify this fraction down here, so let's flip it. So this becomes 2b over 3 t to the 3/2 power. And so there would be my answer. The rocket. Now, if the initial position is 0, what is the rocket's position as a function of time? And I know it's closing time. Let me do this one real quick, but I think it's worth seeing. And we'll still take our break, and then we'll just start lab a little later here. Okay? But the next step is right here. How do you get position? Well, now that we have velocity, you integrate again. You do its antiderivative. So let me circle this and clear the board a little bit. I'm going to say position then is the integral of the velocity And the velocity then is AT minus 2b over 3t to the 3/2, and then dt. And in the interest of time, unless you want me to write all this out, can you see that this is really two integrals? So I'll save a little time and not write them as two, but I'm going to look at this one. What would be the integral of this one? What would you do with that a? Pull it out, and then you'd add the integral of t. So what would that become? So it'd be t, right? You add 1 to the exponent and divide by that new exponent. And then all of these are constants, the 2, the b, and the 3. So let me pull those out of the integration. And now this t to the 3/2 is a power function. So what do? You add 1 to the exponent, so what would it become? Yeah, 5/2, good. And then you would divide by 5 over 2. And then let me not forget, you would add what? Constants. Then you would step back and say, let's interpret that constant. And you can see if time equals to 0, the position would be that constant. So we could call this x naught. But also in the problem they said it starts at position 0. So it would have a value of 0. And so now we can finish by saying it would be this first term. Let me flip this over. So this is going to become a 4b. And 3 times 5 becomes 15. And then t to the 5/2. And so there's the big one I really wanted to show you for anybody who might have a little rusty edges of your calculus. Okay? We're only going to have power functions. Okay? And we'll just raise it to 1 power higher and over the top. All right. Well, this will be a good time to stop. Ron, you can hit off on the camera. And for you guys,